Okay, so hi, I'm Kim Page. For those of you who don't know me, which is probably quite a lot of you actually, I work at the University of Leicester where I'm part of the UK Swift Science Data Centre. So I'm going to tell you a bit about various things that Swift has discovered in the 4.5 years or so since launch. I'm going to be concentrating on the X-ray side of things because I'm a member of the XRT team and therefore that's what I know best. So Peter actually gave you a brief introduction to Swift yesterday, but in case any of you weren't actually listening to him, I should do another one. So Swift, as you probably know, is a gamma-ray based explorer. We have 3 instruments on board: the BAT, which does the detecting of the GRBs, and then the narrow field instruments, the XRT and the UVOT. Swifts can slew very quickly, up to a degree a second in fact, and so it means that we usually arrive on target in less than 100 seconds, which is obviously a lot better than the hours, if not days, that was the case before Swift was launched. And we detect about 100 bursts a year, slightly fewer I suppose, with actually 423 bursts as of the last one that we detected, which was on Sunday. So here's an example of the kind of light curve that we might have seen in the day before Swift. So I've taken 5 hours as a typical example of the follow-up time. We can see that the X-ray light curve looks pretty much just like a simple power law decay here. But if I remove the big black box, you can see what we actually did, the actual X-ray light curve that we saw in the case of this burst, which was 061121. In fact, an extra special thing about this one was that we triggered on a precursor. And so this emission that we see here is actually the prompt emission so we caught most of that with the XRT and UVOT. But if you look at the light curve as a whole, you can see clearly it's definitely not a single power law. So we have steep bits there, a plateau bit there, and then the power law that we would have seen if we'd only got onto it after a few hours. So here I'm just showing a few other examples of light curves to users to demonstrate the things I'm going to talk about. So we have at the left-hand side, the crosses are the BAT data, and the circles are the XRT data. So the BAT data has been extrapolated into the X-ray band so that we can compare complete flex light curves. So what we find is that the early X-ray data tend to join up with the end of the gamma-ray emission. So if we actually have observations which overlap in time, you can see that very nicely. If there's a gap, then you can usually see that they sort of point at each other. There's often a steep power law decline at the beginning of the X-ray stuff. So you can see that in the light curve for 50315 here. And by steep, so I'm talking typically of a temporal decay of 2 to 5 or so. Then following that, we often see this sort of flattish plateau phase. And in amongst all these various phases, we see flares in about 50% of X-ray light curves. So here's an example of a particularly big one for 050502b. And although none of the can't actually see a short burst here, they do show similar light curves to the long duration bursts, including sometimes plateau phases and flares, everything like that. So this is just a parameterization of the example light curves. You have the prompt emission, steep decay, flat bit, normal bit, and then possibly a break to a steep slope that I'll come back to in a while. Although the flare is actually shown on the plateau phase there, we do see them on the steep decay bit and also on the normal decay part as well, so it's not just on the plateau bit. So for the things that I've mentioned, some of the examples of discoveries that Swift has made, we don't necessarily understand exactly what it is that's leading to these things that we see. So this steep decay, do we know exactly what it is, and what's the point? Why do we sometimes see spectral evolution during this phase? What causes the plateau? Is it NAG injection? Could it be the rise of the afterglow? And flares, well, most of them that we see are in the first few hours or so, but we have seen them out to 100 kiloseconds or so after the trigger. So what is it that causes these? The early ones we're pretty certain are due to internal shocks because they have rapid variability and various things that make it that show that they do have an internal origin, but is this the same for the later ones? And so going back to this possible later steepening for light curves, that's the jet break, there aren't as many obvious examples as we might have expected, so what's going on there? So these are the questions that I'm going to go through in a bit more detail now in the next few slides. So the early steep decay that we see in a lot of bursts, though not in all of them, we generally think that this is actually high latitude emission, otherwise known as the curvature effect. So once the internal engines stopped being so active, you can see emission from the off-axis angles. And if this is the case, then we expect the temporal decay, alpha, to be equal to beta plus 2, where beta is the spectral index. If the alpha we measure is less steep than that, if it's a bit flatter, then it could be that we're seeing a combination of prompt and the afterglow emission diluting the rapid decay. But during the rapid decay, we see various different forms of spectral evolution. So sometimes we see in this example in the middle, there's basically no spectral evolution during the steep decay, but sometimes we see it soften, sometimes we see it harden, and sometimes the X-ray emission softens and then seems to overshoot and hardens back up again. Now, if the prompt emission spectrum were just a simple power law spectrum, then that doesn't allow us to explain this all that easily with the high latitude interpretation. However, if we take into account that the spectrum could be a cut-off power law, which is what we tend to use as an approximation to the band function, because our energy band's not really wide enough to constrain things with band function, then that will explain some of the spectral evolution that we see, but possibly not all. Another possible explanation is that it's from a structured jet and there's an angle-dependent spectral index throughout the jet. And one way that could explain the softening is if we're seeing a thermal component which is cooling over time. And later this afternoon, Felix is going to be talking about the possibility of thermal components in the prompt emission. Okay, so following on from the steep decay, we often see this plateau phase. It can't easily be accounted for with an adiabatic evolution of forward shock. Radiative losses would actually steepen the flux decay rather than giving us this pretty much flat phase. So what could it be? Well, there are various possibilities. One popular one is that we're seeing energy injection from the central engine, and Peter mentioned this in his talk yesterday. And there are various ways that this could happen as well. Could be that the central engine is continuing to burble along over time. Alternatively, there could have been, when the burst actually went off, everything could have been emitted with a distribution of Lorentz factors. So the lower Lorentz factors are finally catching up with a blast wave and re-energising what we see, and so making the decay less steep. Variation on the theme, I suppose, is what's called, or often referred to as the late prompt emission. And in this case, you have the central engine continuing to produce shells of decreasing bulk Lorentz factor over time, and then you get internal dissipation leading to the smooth decay. But there is also a completely different possibility, and that is that we could be seeing the rise of the beginning of the afterglow. So this comes from work done mainly by Dick Willingale and Paul O'Brien. And what Dick suggested was that if you take the gamma ray X-ray flux light curve, and in fact this also can be used to model the optical stuff as well, you can actually model the entire light curve with a combination of one or two similarly shaped components. So it's an exponential rise, and then it curves over and relaxes into a power law decay. For the actual prompt emission, we don't say where the rise is, we just start from it's there and then falls over to a power law decay. So here, this is 061121 again, which I showed you on one of the first few slides. I can show you that if you can see the dotted lines, probably a little faint on this actually. That's using this kind of model to model the X-ray afterglow and lower down on the plot the optical as well. And this does seem to work remarkably well for a lot of the light curves. So we usually see that the actual rise of the second component, the afterglow component, tends to be hidden by bright prompt emission. But there are a few bursts where we might actually see the rise before it starts decaying again. And GRB 080307 is a particularly good example. So there's this nice humpy feature of the light curve. So you can actually see it rise before it fades again. And we decided that a good explanation was that yes, that is the rise of the afterglow, and the prompt emission is just dropping off so abruptly. That's why we could actually see the rise. Because if that had been just a little bit brighter, or we'd got onto the burst just a bit later with the XRT, we probably wouldn't have seen that rise. We'd have just seen a very short flat bit before it started fading. Okay. So, next thing I wanted to talk about was flares that we see in 50% or so of the light curves. Now, many of them are fairly small, but GRB, a 50502B did show a particularly large flare. In fact, it has as much, if not more, energy in this flare as there was in the actual prompt emission, which raises the question, what's the difference between triggering on a precursor and seeing the main prompt emission, or triggering on what you think is the main emission and then seeing a giant flare as well? But we do also see them at late times. Oh, and that's an example of a flare at short burst. So we do see them at late times. Some of these could be due to density enhancements in the circumburst medium, but a lot of them are actually consistent with being continued engine activity. So we could have, so the engine's still continuing at 100 kiloseconds or so. Maybe that's also why we see the plateau phase, so energy injection flares related in that way. It's a possibility. So the last thing I wanted to talk about was brakes that we may or may not see in the light curves. So jet brakes are expected if the emission is collimated, which if it isn't if the emission is not collimated, we have trouble explaining the amount of energy that's given out by a GRB. So these should be achromatic. You should see them in the optical and the X-ray at the same time. And we do see some of them in the XRT light curves, but some of us definitely don't seem to show them very clearly. So here's an example of one that does show one, the 60614. There's a jet brake, I'm just showing the X-ray data, but it's in the optical as well. It's a jet brake round about, well, just after 100 kiloseconds. But a 61007 basically has no brake, but we can see from 100 seconds out to 10 to the 6 seconds. So you could either explain that by having a really, really early jet brake, which would mean that the emission would be extremely collimated, so less than a degree for the opening angle of the jet, or a late time one, in which case you have to explain why you got 10 to the 54 ergs or something like that. But as Peter mentioned yesterday, it could be that there are more jet brakes in the light curves than we actually see. And so they're kind of hidden in the data that we have. So sometimes you can see them in, say, the optical band and not in the X-ray, or not clearly see them, or the other way around. But quite often, the data are not inconsistent with there being simultaneous breaks. So it could well be that some of them are just hidden in this way. But then again, we could actually be seeing some breaks which are chromatic, so they're happening at different times across the different energy bands, and there are various possible explanations for these. Could have multiple component jets, so one jet that's leading to the X-ray emission, one that's leading to the optical, or it could be different emission mechanisms, so internal shocks versus external shocks, or reverse shocks, and things like that. Okay, so to conclude, Swift gets onto the burst quickly after the trigger, which means that we get to see what happens in the first few minutes to hours after the actual burst. Which is all well and good, but it has kind of muddied the water slightly and made us realise that there's more to explain than we might have thought pre-Swift. So I showed you the sort of canonical light curve, the cartoon plot, back at the beginning, but as these few examples here show, not all that many light curves actually follow that precisely. So, as is said at almost all GRB conferences in one way or another, when you've seen one GRB light curve, you've seen one GRB light curve. Thank you.
Nice and somewhat extreme conclusion.
Well,
Questions? Yes?
Is there a physical model beyond this suggestion of two components of Orion and Greenville? And do they have some model which explains why the two light curves should look like this, or is it just a...
it's just a phenomenological model. Yeah, I mean, I think that Dick is trying to work out why it could be, but it was just, to begin with, it was just, oh look, we can fit them like this and it works nicely. And so we don't have an explanation why they would be that shape yet. That's something for you theoreticians to work on.
So that model is still, doesn't connect to any hydrodynamics, or that kind of model can explain different behavior in X-ray?
Not that I'm aware of.
Right?
I don't know anybody.
Other questions? Okay, thank you very much. Next speaker is Suzanne Foley, Global Characteristics of Integral GRBs.
I'm going to talk about some of the results that we've obtained on gamma ray bursts detected by the integral satellite. So I'm going to talk about a few specific examples of bursts, and then talk about the general properties of the sample as a whole. So here are the integral instruments. There are 4 instruments on board, 2 gamma ray instruments. So there's the imager IBIS here, and the spectrometer SPEED. And these are supported by an optical monitor camera, shown here, the OMC, and an X-ray monitor called GEM-X, which is here. So IBIS, SPEED, and GEM-X are all coded mask instruments. So these coded masks in order to image X-ray and gamma ray sources. So the coded masks are shown here for IBIS, for GEM-X, and for SPEED, located above the detector arrays. So most of the results I'm going to talk about are from the imager IBIS. So IBIS has 2 detector arrays. So the lower energy detector array is shown here in blue, called ISGRI, and it operates in the 15 kV to 1 MeV image range. Underneath that in green is PIXIT, which operates in the 180 kV to 10 MeV image range. So most of the results I'm going to talk about are just using the ISGRI detector array here. So it has 16,384 cadmium telluride detectors. It has full imaging capability, so it can localize sources to within around 3 arc minutes in the sky. Again, the coded mask here for IBIS is 3.4 meters above the detectors. And this coded mask gives a fully coded field of view of 9 degrees by 9 degrees and a half coded field of view of 19 degrees by 19 degrees. So there are 2 ways in which integral can trigger on a gamma ray burst. So the first way is by looking for GRBs in the field of view of IBIS. And this is because IBIS has a relatively large field of view and good angular resolution in order to localize the gamma ray bursts. And in this way, IBIS detects around 1 gamma ray burst every month to around 3 arc minutes. SPEED also has an anti-coincidence shield, which is, it closes at the volume between the coded mask and the SPEED detector array. So, because the photons aren't coming through the coded mask, it lacks spectral and spatial information. But it does detect 1 burst around every 2 to 3 days, and these occurs are available online. So to date, Integral has detected 62 gamma ray bursts since its launch in October 2002 up to January of this year. And last year we published the first catalogue of integral bursts, which had 46 GRBs. Of these, only 4 have confirmed redshift measurements, shown here, and I'll talk about that in a second, why there are so few redshift measurements for integral bursts. So just a few specific examples. 61122 is one of the brightest integral bursts which has been detected. It had a peak flux of 32 photons per square centimetre per second. And it was the second most intense burst detected to date after GRB of 41219A. The light curve is shown here. SPI light curve has a typical T90 of around 11 seconds. And the SPI spectrum is shown here. And you can see that there's evidence for a high energy component here extending above around 1 MeV in the spectrum. And because of this high energy component, the spectrum is specified by a black body plus a paradox. So this high energy component is specified with thermal component incorporated in a bit. And this high energy component is seen to persist for up to 5 seconds after the main emission is over. So this may be evidence for an inverse Compton component in this burst. GRB 070707 was the first short gamma ray burst detected by integral. It had a T90 of 0.8 seconds, so the light curve is shown here. It had an X-ray and optical afterglow and was located in a very faint host galaxy with an Orban magnitude of around 27. The spectrum is shown here. IBIS and SPI spectra were fit simultaneously for this burst. So here the SPI points are in red and the IBIS points are shown in blue. And it has a typically hard spectrum, so the spectral index of around 1.19, which is typical for a short duration gamma ray burst. And we don't see any significant spectral evolution in the spectrum for this burst. So this is a more recent short gamma ray burst detected by integral. Again, the light curve has a T90 of half a second, relatively bright, peak flux of 3 photons per square centimetre per second. For this burst, there was no afterglow emission detected. Again, typically steep spectrum. This is in IBIS in the 20 to 200 keV energy range. Steep spectrum with photon index of around 1. This burst was also detected by the GBM on Fermi, and it was around 22 degrees from the last war set, but there was no significant emission detected by the batch instrument. So just to move to some of the general properties of the whole sample, this is the spatial distribution of the 62 gamma ray bursts in galactic coordinates. So here's the exposure map in galactic coordinates, where the yellow contours show maximum exposure. So you can see that integral spends most of its time directed towards the galactic plane. And this is mirrored in the burst distribution. So this is part of the reason why we have so few redshifts and so few afterglow measurements for integral bursts, because of the dust obscuration along the line of sight to the galactic plane. So here's the peak flux distribution of integral bursts shown in blue and compared to that of Swift in the dashed line here. And you can see because integral has a much smaller field of view than Swift does, it has much less statistics. So we detect far fewer bursts than Swift does. But of the ones we detect proportionally more faint gamma ray bursts. So at low peak fluxes here. And this is also due to its field of view. So because the field of view is about 12 times smaller, there's a much lower background noise. So we have better sensitivity. So for the bursts that we don't have redshift measurements for, one thing we can do is measure the spectral lag, which can give us an indication of what the luminosity of these bursts might be. So many bursts show a time delay between the arrival of high and low energy photons, where the more energetic photons tend to arrive earlier than low energy photons. So in order to measure this time lag, we cross-correlated light curves in different integral energy bands. So we did this with IBIS data. So correlated light curves in the 25 to 50 keV energy range and 50 to 300 keV energy range. And then the peak of this cross-correlation should give us the spectral lag of the burst. And from previous work done by Norris, an anti-correlation has been seen between the lag and the luminosity for long duration gamma ray bursts, such that the longer lag bursts tend to have lower luminosities. So in principle, this can give us some indication of what the luminosities of these bursts might be and what their distances are. So this is the spectral lag distribution for the 30 bursts in the integral sample for which we were able to do a lag, so that had light curves bright enough in both energy bands for us to be able to do the correlation. And you can see that there are no statistically significant negative lags. So most of the lags are positive in the sense that the high energy emission is coming before the low energy emission is expected. Most of the lags are concentrated here at low spectral lag values, so at around 0.1 to 0.5 of a second. And you can see there's a tail of long lag gamma ray bursts here, extending up to around 5 or 6 seconds. So we split the sample into those with short lags less than 0.75 of a second, and those with long lags greater than 0.75 of a second, to see if there were any differences between the two sets of bursts. So here again is the spectral lag distribution plotted in terms of peak flux. So in the BATSI sample, Norris had found that there was a negligible amount of long lag gamma ray bursts among bright BATSI GRBs, but this increased to around 50% near the trigger threshold of BATSI. And we see a similar effect here with integral, where most of the, all of the long lag gamma ray bursts are very weak, and we don't see any bright long lag gamma ray bursts in the sample at all. So I just plotted here a couple of other low luminosity bursts, particularly GRB 98-425, which is the canonical long lag low luminosity burst, which was very nearby. So this is the distribution of integral GRBs in supergalactic coordinates. So again, the exposure map for yellow is the maximum exposure. And here the bursts are divided into those with long lags, shown in red, and those with short lags, shown in black. And you can see here that 10 of the 12 long lag gamma ray bursts are within plus or minus 30 degrees of the supergalactic plane. So within the half of the sky closest to the supergalactic plane, we get 10 out of 12 of our long lag bursts. And the supergalactic plane is just the plane which contains the local superclusters of galaxies. So it's the local structure of the universe. So it looks like the long lag bursts tend to be associated with this local large scale structure. And to quantify this anisotropy, we measured the quadrupole moment for the long lag gamma ray bursts. So we get minus 0.225 plus or minus 0.090 for the long lag gamma ray bursts. So this negative quadrupole moment indicates that they are more concentrated towards the plane. For the short lag bursts, we get a quadrupole moment which is consistent with 0 and an isotropic distribution. And just another thing to note that the supergalactic plane is not very well defined. So its extent isn't really known, but we think that superclusters are out to around 400 megaparsecs. So to get some idea of what the distance scale to these bursts might be, there are two reasons why a burst might be a long lag burst. So typical GRB lags are about 0.1 of a second. So you could have a long lag burst if it was a typical short lag gamma ray burst with just a very, very high redshift, so that the lag was redshifted to a higher value. Or it could be an intrinsic property of a long lag burst. But the number of very high redshift bursts that we expect in the integral sample has been modelled, and we don't expect there to be more than 1 or 2 high redshift bursts in the whole sample. So this doesn't seem to be able to account for all of the long lag bursts that we see. So if we assume that the lag is an intrinsic property of at least some of these bursts, we can get an idea of what the distance to these ones might be by looking at previous low luminosity long lag GRBs which have distance measurements. So GRB 98-425 had a long lag and was at 36 megaparsecs, and a 60218 had a very long lag and was at 145 megaparsecs. We also know that weak Baxi bursts are correlated with galaxies out to around 150 megaparsecs. And taking into account this association with the supergalactic plane, we've adopted a distance of around 250 megaparsecs for these bursts. So we calculated the rate of these bursts using the 8 long lag bursts which were detected in the partially coded field of view of integral of Ibis, which was around 0.1 steradians. If we assume that at maximum 2 of these are at very high redshifts, and we adopt a distance of 250 megaparsecs for the remaining 6 bursts. So if we calculate a rate using these assumptions, we get an all-sky rate of around 2,500 per cubic gigaparsec per year, which has a very large uncertainty because we're just assuming this distance factor. So if we take this value as the rate of these long lag, low luminosity bursts, it far exceeds the upper limit of 300 per cubic gigaparsec per year of type 1bc supernovae, which are thought to produce gamma ray bursts, if we assume that all of these low luminosity bursts do produce a supernova. But we also know that not all bursts do produce supernovae. For example, there's a 60505, which is apparently a long duration gamma ray burst, has a relatively long lag, but doesn't have an associated supernova. So there may be some, if these bursts are associated with the supergalactic plane and with superclusters of galaxies, then there may be some differences in the environments of these clusters which are producing a different kind of gamma ray burst, and that there is a different progenitor for these low luminosity long lag bursts. So just to summarise, Integral has detected 62 bursts up to January of this year. It provides fast and precise localizations for around 1 burst per month to the community. Integral and the resulting follow-ups can yield interesting results for both long and short gamma ray bursts. Because of its very sensitive Ibis detector, Integral detects proportionally more faint gamma ray bursts than Swift does, and this allows it to probe this low luminosity population of bursts. 12 out of the 30 bursts for which we were able to measure a lag had long lags, greater than 0.75 per second. And these bursts seem to be faint. They have long, slow time profiles, and if they're associated with the supergalactic plane, then they appear to be low luminosity bursts, which are different from the high luminosity population. Thank you.
Is there any evidence in the Batse population of long lag bursts to be associated with the supergalactic plane?
Yes. Yeah. They see a similar effect for long lag bursts to about the same significance that we do. The quadrupole moment is about 2.5 sigma level, the same as us.
What is the energy with this burst? What's the total energy with this burst, this long lag burst corresponding?
Of these bursts in general?
No. Assuming that you have a distance of 215
Yeah.
megaparsec, what is the typical energy?
It's very similar to 98 to 425, about 10 to the 48, 49.
So this will be the observation of 0602 in June suggested that there is if you take just this one event, there is a very large population of extremely geodes.
Yeah.
But now you're having here another very large population of much stronger geodes. There are about a factor of 100 stronger than this extremely weak one.
Yeah,
There's still low luminosity.
yeah, and they do seem
There's
very
still low
similar to,
luminosity.
say, 98 or 425.
Yeah, it's a huge population. There was another question, yes?
Yeah, there's a, the furnace, there's also found that the very high energy in the black button seems to lag behind the lower energy material, so it seems to be contradictory to
Yeah.
define. Would you like to comment on that?
Yeah, I don't know much about Fermi results, but definitely in the lower energy range, in the typical 20 to 200, 500 energy range, it's always the other way around.
Is there any indication for that in the GBM?
Oh, I don't know. I mean, it's an obvious thing to do.
Yeah?
One more question. Did you check if this is consistent with no detection by Swift of any such origin?
We've looked at the SWIFT data, but in terms of lags, we can't do the lags for the very weak SWIFT bursts because of the sensitivity.
Not in terms of lags, in terms of redshift. Swift did not detect any object like this. Not even a single object in this range. So is your result consistent given the sensitivities of the both detectors and this sky coverage and so on, that Swift will not detect anything and you have so many errors?
Well, I suppose the 602 gene is the only one that I can
No, 602 was a different object. This was much weaker than
I
this.
haven't.
This was much weaker than this. My guess is that there is inconsistency between the two statements. That there are so many good bursts at 10 to the 48 and they simply not detect anything. So it's a guess. I didn't do the calculation.
Okay, well,
It's something that you should check.
Yeah, definitely. But just our energies, there is a huge uncertainty there as well. You know, I'm not saying that all of these have 10 to the 48 because we don't know the distances. So there's a huge uncertainty in that energy. We're just saying they're very.
You're suggesting that there was a new population of bursts. And so the question is it consistent with what we know on the redshift distribution?
Yeah,
I'll show one graph tomorrow which I think is inconsistent.
Other questions? Okay, thank you very much.
Can you like double click?
Okay, so the next speaker is Kazutaka Yamaoka, and he's going to tell us about the Suzaku observations of both gamma ray bursts and soft gamma repeaters. Thank organizers for inviting me to this conference. Today I'd like to talk on Suzaku X-ray and gamma ray observation of gamma ray bursts. My name is Kazu Yamaoka from Aoyama University in Japan. Here is an outline of my talk. First, I will introduce the Suzaku X-ray satellite and the wideband whole sky monitor 1. Then I will show some results from X-ray afterglow observation with Suzaku. The third one is main topic of my talk about Suzaku observation of prompt emissions. I will mainly talk on the spectral and timing properties of entire GRB emissions and individual pulses. Finally, I will conclude with a summary. I will begin with an introduction of Suzaku X-ray Observatory. Suzaku was launched on July 10, 2005. The advantage of the Suzaku is broadband coverage of 0.2 to 600 kb. So, and it also has a very low background and good energy resolutions. Suzaku carries two kinds of narrow field instruments on board. One is the X-ray CCD camera, XIS. 4 XIS located at each focal plane of X-ray telescopes. And the other is a hard X-ray detector with non-imaging capability. This is a hard X-ray detector which has an energy range of 10 to 600 kb. And in addition, we have a wide field instruments, wideband Oscar monitor. And the worm is a subsystem of the hard X-ray detector. This is a schematic view of the hard X-ray detector. The worm is lateral large VGO shield of the hard X-ray detector. It works as not only a shield but also an Oscar monitor. The scientific objectives of the worm are GRBs, soft gamma ray repeaters, solar flares, and black hole candidate with an Earth occultation technique. The one key parameters are shown here. The energy range is 50 kV to 5 MeV. The field of view is about half of the whole sky. The geometrical area is per one side from this direction is about 800 square centimeters. The important feature of the worm is a large effective area. This figure shows a plot of effective area as a function of energy. The worm has much larger effective area than those of any other gamma ray burst monitors. So using the Suzaku satellite, we can observe the gamma ray burst with two methods. One is the X-ray afterglow observation with narrow field instruments, and the other is prompt emission observation with Suzaku 1. The scientific motivation for X-ray afterglows is detection of hard X-ray emissions above 10 kb. And we will also perform a detailed study of the plateau phase and its change to normal decay phase. And the confirmation of presence of emission or absorption line features are also important. For prompt emission, we will investigate the spectral parameter distributions such as E-peak and photon index. This is about the E-peak distribution. As you know, the E-peak is concentrated around about 300 kb. And the various correlation using many GRBs with known redshift in the Swift era should be verified. And we will also perform the temporal studies using the large 1 GRB sample. And here is a summary of X-ray afterglow observation. We organized a GRB-TO team for quick repointing and trying to start a TO observation within about 3 hours after the Swift trigger. This is a typical XRT light curve. 3 hours are shown here. 3 GRB TO observations of Swift GRB so far. And the earliest observation time is 3.3 hours in case of GRB 070328. However, we do not succeed in detecting hard X-ray emissions above 10 kb. We will show some results for 2 gamma ray bursts. The first case is GRB 060105. Suzaku observation starts at 5.3 3-5 hours after the shift trigger and observe the late time afterglow, that we detected no emission, no significant hard X-ray emissions, and no clear emission lines in the X-ray CCD spectrum. A combined Swift Suzaku light curve indicates early jet light break around 1 hour, like this. The other is GRB 060904A. Suzaku observation starts at 9.4 hours after the shift trigger. And also Suzaku sees the late time afterglow. The spectrum is consistent with the late time afterglow, which has a photo index of around 2. Okay, this is the results for X-ray afterglow observation. The next topic is about the prompt emission observation. It's Suzaku 1. The one here is a summary of event list from August 2005 to April 2008. 538 GRBs confirmed by other satellites, and we also have we also detected possible GRBs. This number, judging from the shape of the light curve and so on. Using this number for confirmed GRBs, we are now detecting at least 140 GRBs per year. This is a duration distribution for the one GRB sample. Dotted line shows a BATSI sample taken from BATSI 4B catalog. As you can see, the one sample shows a bimodal distribution, which is similar to the BATSI distribution. 104 GCN circulars were released so far. 74 pores about one spectral analysis and 22 IPN localization. So this slide shows the capability of the Suzaku 1. Left panel shows an example of 6 bright GRB spectra. As you can see, high quality spectra can be obtained for bright GRBs up to 5 MeV. And the light panel shows a correlation between isotropic luminosity and peak energy in the source frame for GRB 061007. Each point shows results from time-resolved spectral analysis for every 1 second time being. As you can see, we can see a very clear correlation, except for rising phase of the burst arcs. So high statistics in a short time is very important in determining the origin of emission mechanisms. The first main topic of the one is spectral parameter distribution using the BAT and WAM sample. This result is submitted to APJ on this April. The sample contains 86 bursts, including 35 GRBs with non-redshift and 6 short GRBs with non-redshift. The range of the redshift is like this. Here is a distribution parameter for distribution for the spectral parameter, lower energy, lower photon index alpha, higher photon index beta, and peak energy D peak. The median value in our sample and the BATSI sample are shown for comparison. As you can see, our WAM sample is very consistent with BATSI sample. although the E-peak distribution is slightly broader than Batsy sample. And we will show the E-peak and the ISO, so-called amaturations for BAT1 sample. Red one shows long GRBs, and blue one shows short GRBs. For long GRBs, clear correlations is verified in BAT1 sample, except for low luminosity GRB 060505. For short GRBs, as shown here, most of the bursts are outliers of these relations. And the next topic is about time-resolved spectroscopy for 12 long bursts with long redshift. This work has been done by Satoshi Sugita in his PhD thesis. We divided 1 GRBs into individual pulses and performed a time-resolved spectroscopy for each pulse. The sample contains 6 GRBs from BAT1 sample and 6 GRBs from HT2 sample, and consisting of in total 63 pulses. This is a correlation between the E-peak and isotropic luminosity for 63 pulses. Most of the data with high energy E-peak is taken from BAT1 sample, and lower E-peak data is taken from HT2 samples. A clear correlation is found for pulses in a very wide luminosity range. The correlation is expressed by this equation. The power is about 0.51. This is consistent with 0.5 from synchrotron emissions. And we also plotted a short GRB sample on the same plot. Dotted line shows the 3 sigma lines from the best fit parameters. 5 short GRBs are within 3 sigma errors of EP error isolation for long GRBs. So this result shows that some short GRBs might have similar origin to long GRBs. The final topic is timing properties for prompt emissions. We have analyzed 102 GRBs. We first analyzed the entire prompt emissions. The soft lag is measured by cross correlation function between the 2 energy range. This is a correlation between P90 and spectral lag. As you can see, we can clear 2 separated branches, and one is a GRB with a single pulse like this, and other one is GRBs with multiplied spiked pulse like this. But we divided the one GRBs into individual pulses. We can see a very linear correlation between the pulse width and the spectral lag. The pulse width is measured by correlation function. The relation is shown here. Timing property of the short GRBs seems to be very smoothly connected with long GRBs. And also, this is a duration. This is a lag distributions for short GRBs and individual pulses, and the tau distribution get more similar to short GRBs. So this is a summary of my talk. So that can observe the X-ray afterglows and the prompt emissions. And the main result is that the spectral lag and the EPR isolation in the individual pulses of long GRBs not inconsistent with short GRBs. So we suggested that short GRBs might have a similar origin to those of long GRBs. One possible scenario is that central engine produces many patchy shell structures. When we see just one patchy shell in the line of sight, this is long burst. This is a short burst, and the other ones are long burst. Thank you. Finally, we advertise a Maxi instrument. The Maxi will be launched this date. So Maxi is a very sensitive X-ray on sky monitor. We can observe the X-ray flash and micro quasars and AGNs. Thank you.
So we have time for a few short questions.
I have a question about solar flares. You mentioned that you detected quite a number of solar flares, right?
Yes.
Do you have a spectrum? And if you do you see spectral evolution during the flare itself?
Yes, we observed a strong flare on 2005, and we analyzed one data of 100 kV. The power index is about 4.
But it evolved during the flare, spectrum evolved, or?
Yes, I'm not sure, but spectral evolution is found in the one data. But I'm not sure.
Short technical question. Like the afterglow that you got, like, for how long did you measure?
About a typical one day observation.
Is it up to 1 day? I didn't get it.
Yeah, our Suzaku exposure time is about one day.
This is not strictly related to gamma ray burst, but PET-C could be used to monitor persistent sources thanks to Earth occultation technique.
Yes.
Is it possible to use one with the same technique?
Yes. This is sorry. This is an example of the light curve taken by Suzaku-1 for signal 6-1, and a comparison with SwiftBat and RxTO sky monitor. But for signal, our detector has a low detection sensitivity, so this work has been done for only signal 6-1 and the Crab Nebula, for some other sources.
Okay, let's thank the speaker again. Okay, so next up we have one of our hosts, Sinead McGlynn, and she's going to tell us about new results from the Fermi Observatory, new GRB results.
Thanks, Peter. Okay, good afternoon, everybody. As Peter said, I'm going to talk about GRBs with Fermi on behalf of the lab and GBM collaboration. So just to start off, with the situation before Fermi was launched. There was relatively little known about GRB emission above 100 MeV. Previous observations by Egret had previously observed 94-217 and 94-1017, and Adelaide then recently published a paper on 080514B. So we knew that there was a possibility of extended high energy emission several hours after a burst occurred. We knew that there was a possibility of high energy emission shortly after the burst, extending afterwards, and also possible simultaneous high energy emission. So these basically require maybe more than one emission mechanism, and were basically one of the unsolved problems. So what was needed basically was more sensitivity and larger field of view. So, as Julia already talked about, Fermi described a lot briefly, so I'm going to do the same thing. Just a comparison between some LAT parameters and some EBIT parameters. So, basically, LAT has a wider field of view, a much smaller dead time, so it's possible to study short bursts, a larger effective area, better angular resolution, especially at higher energies, and then increased energy coverage, so up to above 300 kilometers or so. So all these factors will basically help to discover more GRB. So Julia already showed this typical prompt GRB spectrum. So GBM, the GBM energy ranges appear in red, and the LAT is in grey. And just for comparison, I put Swift down here as well. So it wasn't sure which way it wasn't clear which way the high energy emission would go. If it would tail off or it would keep going. But hopefully with Fermi, the plan was that we could detect emission from both the prompt and the afterglow phase. We could also follow up high energy emission of GRBs from other instruments like Swift, I think, or Suzaku, and with high resolution of these high energies. So to date, GBM has observed 192 GRBs, around roughly 200, with 17% of these being short bursts. And this plot here just shows the angle, the LAT angle, as a function of the fluence between 8 and 1000 kV. So that's what most of them are 8, between 8 and 1000 kV. So that's the quoted fluence from the GBM GCNs. So the LAT bursts are all here in red, and so you can see that they are generally the brightest GBM bursts, with the exception of 81024B, which is short. And then there was one that was seen at an off-axis angle of about 86 degrees, 081215A. So it is possible that you get some events coming in basically through the design of the instrument, but obviously these are harder to analyse. It takes a little bit more work. So the LAT predicted rate initially was very much dependent on the spectral parameters. So if you had the average burst, or if you assumed that basically the high energy photon index, that there's the high energy photon index basically kept going, so there's extra emission. So depending on the value of beta, we got different estimates for the predicted rate. But to date, there are 8 definite detections, and so we expect a few GRBs per year with more than 100 counts. So as of the middle of May, this is a plot of all the GRBs on the sky. So the blue stars are the 8 LAT GRBs, the black and red are all the GBM bursts, with the red being the ones that were in the field of view of the LAT, and the black ones being the ones that were outside the field of view of the LAT. So we have a list up here of all the GRBs that have been detected so far. So we have 2 short ones, 081024B and 90510, which we're not allowed to talk about yet. And I'm going to talk about the first 3, so 080825C, 080916C and 081024B. So 080825C was the first official detection by LAT, and we got 14 events above 100 MeV. So the light curves here, the green is the GBM, so it's the sodium iodide detectors, which are the low energy ones. The middle one is the BGO detectors, so there's 12 sodium iodide, 2 BGO. And this is the BGO light curve, which goes up to about to a couple of hundred MeV. And then the last down here, so the red is the light curve, and then the event energies are plotted as well, so there does seem to be evidence for a long-lasting emission after the burst seems to end in the MeV range. But the fit is consistent with a band function all the way up to the end of the lock points, basically. But this is preliminary. 080916C, some of you may have seen this a few times before. So again, this is these are the light curves. So the top one is the sodium iodide. So it had a T90 of about 66 seconds, which goes to right here. Then we've got the BGO, which also is, and then this light curve is all of the lat events. So before there was any cuts made in the data. And then these are the events that were above 100 MeV, and then several events above 1 GeV as well. So this is quite a strong burst, and there was a signal recorded in 9 of the sodium iodide detectors. So there was a photometric redshift calculated by ground to be 4.35, and it's the first GeoB with high energy and no redshift. So what we've done here is split up the light curve into 5 separate intervals. So we've got A, B, C, D, and E. And you can see here the inset shows interval B just zoomed in. And you can see that there seems to be, the emission seems to be moving towards later times as you go towards higher energies, which is a signature of spectral evolution. So the spectral parameters are here from the band model fit. So you have alpha, the low energy power law index, beta, the high energy power law index, and peak energy. And you can see that it's going from soft to hard to soft evolution. Well, these two don't evolve very much, but e-peak evolves quite a lot. And so the reason that it's soft at the beginning is because basically the lat, there was relatively little emission at the very start. So the lat emission is more consistent with the second GBO. So it goes from soft to hard to soft evolution, and these are the spectra plotted in new space for each of the time intervals. So you can see that the change in the spectral slopes only occurs between A and B. So you can see it here as well. So because we had we could basically use the spectral parameters to make some theoretical constraints. So we can use, we assume an optical depth of unity, you can estimate the minimum Lorentz factor for each bin. We estimated minimum Lorentz factor of 600 for bin D, which is this one, and Lorentz factor of almost 900 for bin B. Bin B is the one where it's highest, which is much higher than any previous constraints. For example, from GeoB mentioned in 23. We could also estimate a limit on the quantum gravity mass, because the quantum gravity high energy photons could arrive to us at different times, low energy photons. So we decided we'd put a very conservative lower limit. So because the highest energy, lat event arrived 16.5 seconds after the trigger. So we could use this estimate, or we could use this time difference. So the time difference is related to the change in energy, which gives you an estimate on the quantum gravity mass. So it's the most stringent limit that's been obtained so far. So then GeoB 081024B, which is a short burst. So you can see up here, it has a duration of about 0.8 seconds or thereabouts. But so the layout is the same again. The light curves are going from in order of increasing energy. So you can see that there's definite extended emission at GeV energies. There's a lock detection at the 8.5 sigma level, and the spectrum for this one is also consistent with a band function fit. So even though it's still over quite a large energy range, it's still a band function fit, so there's no evidence for any extra components at the end. And again, the main peak of the LAT emission is consistent with the sort of the second GBM pulse. So in fact, I'm actually flying through it all, I apologize. So my conclusions, so LAT and GBM are working extremely well together. It's been 200 bursts detected by the GBM with 8 LAT detections. There's evidence in most of the bursts for delay between the MEV and the GeV emission. The band function provides a good fit to most of the bursts so far, with no need for any additional high energy components. And all of the bursts seem to show significant emission extending beyond the observed MEV emission. So possible consequences of this are that it must be a very narrow correlation relativistic jet. We still don't know exactly what sort of origin, whether it's a leptonic or hadronic origin for the emission. But we can use several different parameters to estimate some theoretical constraints. And as Judy said already, the LAT data will be publicly released at the end of this summer, and the data is available along with science tools through the Fermi Science Support Centre. So that's it.
I'll be time for plenty of questions.
The estimate of the Lorentz factor is based on the opacity argument, so you only require that the energy in the common frame is below LC squared.
I'm not entirely sure. I think Judy what was the question?
No, it says it's a calculation using the spectrum as well. So,
Yeah.
so it's not sort of a zero order calculation. It's more elaborate.
So if it's 300, then flux is suppressed by a factor of few.
No, it's 600 to 800.
That is for the requirement that the optical depth is less than unity.
Yeah, unity. Yeah.
Unity.
Yeah.
Can be a little bit higher with some attenuation factor. Is this your question? That you can assume a little bit higher optical depth with some attenuation.
Yes.
Still have some
Well,
yeah, I mean the EBL was played with as well, but we took EBL stacker high, stacker low, so this is the most conservative estimate.
Out of the 200 bursts detected by GBM, were all of them possible to observe with LAT? That is, LAT could read point to observe them, or were some of them not observable?
No, well,
That's
no.
What fraction of those that LAT could see did it actually see?
Okay. So here it shows, you can see the red points are the ones that were actually in the field of view at the time that the LAT didn't see, basically. And then the other ones, the black ones, are the ones that were out of the field of view. So it looks to be sort of
About 50-50.
50-50, yeah. So you can organise an AOR, an autonomous repointing, but it's only really as if the burst appears to be a burst of interest, basically.
Okay.
You can't do it with all of them.
Okay, so it looks like roughly 1/10 or so.
Because if it's in the field of view, it should have seen it, right?
Yeah, yeah.
You can get calculated just looking at comparing the field of view of the two instruments. The lab has a field of view of 2.4 steradians and the GBM is at 9.
So it looks like about one-tenth of the one that back that it detected it did.
Can you show the previous graph?
Or it did detect about one-tenth of the one.
It's about right. It's a little bit, yeah.
Yeah, in order, yeah.
So it seems that there are very bright, now these very bright bursts which are not seen by large in the field of view of black.
Like
You
say,
see, there's a clear energy dependence here.
yeah.
On the black is detecting only the brightest bursts. But there are a few very bright bursts which have not been detected.
Yeah.
Now, do you know if those were in the field of view?
Well, okay, so the limit of the field of view is this line here. Sorry, I should point that out. So it's about
Oh, this
70
line is the
degrees.
field of view.
Yeah.
So there's only one bright burst
Yeah.
that is in the range. So you can basically take a rule of thumb that on this diagram, if the burst is more than 2 times 10 to the minus 5 hertz per centimeter squared, it will be detected by lab, and there is only one exception.
Yeah, yeah.
And this is consistent just with the extrapolation of this energy with beta of about minus 2 point something to the lab energy. So it's clear that there is no extra transformation. From this graph, it's clear that there is no extra transformation. Is this also preliminary and unpublished, this figure?
There's nothing secret about this.
Yeah, it's not secret.
If
No.
there's anything that...
Most of Fermi data is secret. Don't say there's nothing secret. All of Fermi data
This
is
one-
secret.
Yeah, but anything we show at a meeting is not, if we show something as a plot at a meeting, it's...
Yeah,
it's
I mean,
available
this
for
one I updated recently, and it's just information from the GCMs. So it's basically that somebody was keeping a table of the reported fluences and the reported angles. So the GBM circulars will always say the lat angle. So this is, anybody could create this.
Something worth bearing in mind with this, though, is it's fluid, so it's integrated over the duration of the burst. So
Yeah.
it's not a surprise that 08 to 10, 24 is low. If you make the same plot but with peak flux, then that rises right to the top.
Yeah, exactly. Yeah, so like all the ones, these ones, for example, like they're all long bursts, so that would factor. And also some of these, the fluents, I guess probably the ones at the bottom, the fluents was quoted initially just between 50 and 300. So it needs to be updated so that the fluence is consistent with all of them. But the vast majority of them are between the 8 to 1,000 kV range.
So you must know how much energy is in each of these 8 bursts was coming out with very high energy.
We have a plot of showing the ratio of the energy and the MEV and GEV ranges. That's what you're asking, how we extrapolate for the detected burst.
When Fermi went up initially, there was lots of plans to get it to work with Swift. How's that working out? Roughly how many have you observed that Swift also observed?
I don't know the exact number, but there have been, I don't think any of the lab ones were observed by Swift.
Well, not simultaneously. Some of them were observed a little later.
Yeah, exactly.
Yeah, but I mean simultaneously how many have you got joint spectra for? Roughly.
I think that was like sorry?
I went to 810.
Yeah, it's not very uncommon to have both GBM detections. I mean, they're both instruments that have a wide field of view, and since the GBM sees the entire unaffected sky, if it's possible to have an overlap, there will be one.
Yeah.
Because GBM is not pointing anywhere, and I suppose you could tilt a little bit to get the overlap. The really key thing for the overlap is to get more lap bad detections, because that's the only path to getting early afterglow observations of black detected bursts. I mean, we're just being quite, I mean, I think at this point it's almost unfortunate to have 8 detections that don't have a simultaneous map trigger. I mean, we've just dice falling in the wrong place.
Okay, let's thank Sinead again.